Hey guys, welcome to another physics video, and this time we're going to be talking about relativity, a topic mainly built upon by Albert Einstein and Hendrik Lorentz during the early 20th century. And what I'm going to do in this video is basically demolish the existing misconceptions and general understandings of time. And it mainly starts with this one principle, that the speed of light is a constant for all observers in any fixed medium. What do I mean by that? Well, let me show you. Right. If we look at two cars which are moving, and if we take it from what we call a stationary perspective, or let's say there are two lamps shining down on the cars, and these two lamps are staying still. And since these two lamps are not moving relative to us, that means we are also standing still. We can see that the velocity of the blue car is 2.5 meters per second, and the velocity of the orange car is 5 meters per second. The orange car is moving more quickly than the blue car. And of course the velocity of the lamps is 0 meters per second because they're stationary. But that's only because we're standing with the blue lamps. Standing with the lamps. What if we decide to hop inside the blue car? What are we going to see? What we're going to see is that the blue car is now traveling at 0 meters per second, simply because our perspective is from the blue car. As it moves, our perspective shifts. So the relative velocity of the blue car, that is the velocity of the blue car to us, now becomes 0 meters per second. And now the velocity of the lamps is minus 2.5 meters per second, only minus because it's moving in the opposite direction. And as we can see, if we hop inside the blue car, our perspective of reality completely changes. Now the lamps are moving. You could, of course, argue that the lamps are not moving, they're in fact standing still, but it's you which is moving. But remember, there is no such thing as absolute rest or absolute motion. An object is not standing still just because you perceive it to be standing still. If you throw a ball, the ball moves relative to the earth. But the earth also moves relative to the ball. And in this case, even though the lamps could be argued to be standing still, they're moving relative to the blue car, just as the blue car is moving relative to them. Now, we can see that the orange car is also moving, however, it is moving at a slower velocity, and this is what you see. When you're on the road, sitting in a car, and you look at the other cars beside you, they are still moving. However, their velocities will be slower, because you are also moving. So now what we see is that the velocity of the orange car is only 2.5 meters per second, as opposed to 5 meters per second before. Now, what if we take it from the perspective of the orange car? What we see is that the lamps are moving backwards, but this time much faster. Now their velocity is minus 5 meters per second. And now the velocity of the blue car is minus 2.5 meters per second. It is going back. That is what you see on the road when you're inside a fancy sports car and decide to zoom ahead of the rest of the cars. You see them going back, when in fact, relative to the pedestrians and the sidewalk, they are still moving forward, but they're moving slower than you. So you see that they are moving back. And that is kind of the basic principle of relativity. There is no absolute perspective or absolute velocity. If you see something is moving, its velocity that you see will be its velocity relative to you. For example, when a car moves across the road at 40 miles per hour, it is not actually really moving at 40 miles per hour, because the Earth is also spinning, and the Earth is orbiting the Sun, and the Sun is orbiting the galactic core. What you are seeing is the car moving at 45 miles per hour relative to the Earth, and relative to you. Alright, now this should be relatively easy to understand. There is no such thing as absolute rest or motion, everything is relative. That's done and dusted. However, here comes the catch. The same does not apply to light. And this really does contradict our basic understanding and common sense, but then again, all 20th century physics did that. It contradicted common sense. If we take it from the perspective of the lamps, the light would be traveling at a speed of roughly 300,000 kilometers per second. It would just keep going and going and going. And then if we take it from the perspective of the blue car, it would still be going and going at the same speed. And then even if we take it from the perspective of the orange car, it would still just be going and going at the same speed. This appears to not make sense, and in all honesty, it does not really. So what does that mean? Well, let's say we've got a car which is standing still, and it is shooting off a beam of light from its headlamps. The car's velocity v is now 0, and the time it takes for the light to travel to this point is t. So you consider the total distance is ct because it's just speed times time, and the speed of light is c. Now, what if the car is moving when it shoots off that bit of light? We know that if we throw a ball, it moves at a certain velocity. Now, if we're standing on a train and then we throw the ball's velocity will be its original velocity plus the velocity of the train because it's already moving. So this distance should be v plus c all times t, because v plus c is the resultant speed, the speed of light plus the speed of the car, multiplied by t, which is the time, to get us the complete distance. Now, in a stationary perspective, which means if we're just standing still, the distance traveled by the light will be greater in v plus c times t, because v plus c times t is greater than just c times t. And we know that, so we know that the distance is greater. The distance traveled will be greater. But we also know that the speed of light is actually the same. Well, if we look at the equation distance equals velocity times time, and we know that distance has increased, I think that says t, so that should say distance has increased. Distance has increased, but velocity has stayed the same, then we know that t must be greater as well. Time must have increased to accommodate that increase in distance. So the time experienced by somebody standing still, as opposed to somebody moving, is greater. In short, time passed for a stationary observer is greater than time passed for a moving observer. Or to paraphrase, you age slower when you move faster, which is extremely interesting. Right, now I'm going to go a bit into mathematics here. We do know that as you go faster, the passage of time speeds up, kind of. But how much does that, how much is the effect? What is the magnitude of the effect? Well, this can be shown mathematically using what's called an Einstein clock. I do understand that some of you might be a bit uncomfortable with the mathematics, so I will post time in the annotation somewhere to skip it. However, it is unrecommended. I do think that it is good to look at the maths and get a clear understanding, but I do understand that it may make some of you uncomfortable, so just skip to that bit. Okay, now what is an Einstein clock? Well, let's imagine there are two mirrors, and there is a beam of light constantly going from one mirror to another. It's constantly bouncing and bouncing and bouncing, up and down, up and down, up and down. Now, if we're talking about the passage of time, we do know that the passage of time varies between different observers of different velocities. So let's call the time that the clock experiences to be t, and the time that a stationary guy called Bill experiences to be t primed. Now, if we imagine that instead of standing still, these mirrors and this clock in general moves to the right with velocity v, then we could show that the light, instead of taking a vertical path, does take a diagonal path, and its distance would be c times t prime. Because remember, this diagonal path would not be seen by the clock. The clock would still think that the light is traveling vertically, but for Bill, who's stationary, who sees the clock moving, he sees the light to be taking a diagonal path. And so, since t primed is Bill's time, this distance of the diagonal path is c times t primed. Now also we have got ct. Now this is the vertical distance seen by somebody inside of the clock. Just c times t. And there's also v times t primed, which is the distance traveled by the mirror as seen by Bill, which is just basically the velocity of the clock multiplied by t primed, which is the time that Bill experiences. Now we can see that this is indeed a right-angled triangle, in which we know that c times t prime all squared equals v t prime all squared plus ct all squared. That's just basically the Pythagoras rule. Hypotenuse squared equals the sum of the other side squared. So we can rephrase that to say c squared times by t prime squared equals v squared times by t prime squared plus c squared t squared. And that's just a basic rearrangement or a basic rephrasing. Now we can divide everything here by c squared. So what we get is t prime squared equals v squared over c squared t prime squared plus t squared. Alright, now that we've got that, we can rephrase it by just putting all the t primes to one side and the t to the other side. So it becomes t squared equals t prime squared minus v squared over c squared times by t prime squared. And once again, that's just a basic rearrangement. Once again, feel free to pause this video if you want to copy down these equations. But anyway, now that we have that, what we can do is we can rearrange it once again just by factorizing the right side of the equation. So this becomes t squared equals t prime squared multiplied by 1 minus v squared over c squared. Now what we can do is square root both sides. So we get t equals t prime times by the square root of 1 minus v squared over c squared. Now once again we can rearrange that by putting the t prime on the left side, and it becomes t prime equals t over the square root of 1 minus v squared over c squared. Now here's the equation in all of its glory. The stationary time, which is the time experienced by Bill, equals the moving time, the time experienced by the clock, divided by the square root of 1 minus v squared, which is the velocity, the relative velocity, I should say, of the clock, divided by c squared, which is the speed of light squared. What does this mean? Well, this basically means that there is actually a shift. Both observers do not experience the same time. But how come we do not use this equation in most aspects of everyday life? Why don't we see this effect? Why does it go past unnoticed? Well, as we know, c is huge. The speed of light is massive. Einstein called it the universal speed limit, the limit at which anything can go. So we know that it's massive. And usual velocities in our everyday world are small, such as the velocity of a ball or a car or even a spaceship. Compared to the speed of light, they are tiny. So we know that v squared over c squared is practically zero. Not exactly zero, but practically zero. So 1 minus v squared over c squared is practically 1, because that's basically just 1 minus 0. So we know that the square root of that is practically 1. So we know that t over that, which is practically t over 1, is practically just t. And since this is the whole right side of the equation, we can say that t prime is practically t, which is why we don't notice this effect, because it is so minusculely tiny in our everyday world. T prime is practically t for everything that we experience in our everyday lives. However, when you get to speeds near the speed of light, where v isn't so small, such as in the Large Hadron Collider, they accelerate particles to 99% the speed of light, that's when this effect becomes truly apparent and important. Alright, basically what this equation says is that if we want to travel faster into the future, c always has to be greater than v. Remember how I told you that you will age slower? What you're effectively doing is traveling faster into the future whilst keeping your internal time the same. And for that, c must still be greater than v, but v must be above 0. If you want to stand still in time or freeze time, c must equal v. Let's take a look at that equation again and see why. If c equals v, then then v squared over c squared is 1. And 1 minus 1 equals 0. The square root of 0 is 0. T over 0, well, you're dividing by 0 there. That's practically infinity. So that's how you can tell that you have infinite speed, basically. You're freezing time. You can go anywhere you want. And that is what a light ray feels. So then you might ask the question, how come light rays do have a finite speed then? How come when light travels, it doesn't zip to the other side of the universe in an instant? This equation says it has infinite speed, so how come it has a finite speed? Well, I'm going to tell you that in a second. I'm going to tell you why, using a concept that I like to call time bubbles. Alright, and if you want to travel back in time, that does require c to be smaller than v, which basically means you have to travel greater than the speed of light. And that is impossible. It would take an infinite amount of energy. So that's how we can tell that it is impossible to travel back in time using this method. Another method may be created, but we cannot travel back in time by traveling faster than the speed of light. Alright, now that we've got that down, let's talk a bit about this concept which I alluded to earlier, which is time bubbles. Now, no information can travel faster than light. No information. What that means, effectively, is that if the sun were to immediately disappear, we would still orbit where the sun used to be for another 8 minutes, because for another 8 minutes, the Earth doesn't know that the sun is no longer there. And if it doesn't know that, then it cannot physically react to it, so it's still going to orbit in its previous path until it goes off on a tangent. The same as which I may have said before, if a black hole immediately just forms itself in the center of the universe, let's say, but basically it will not immediately attract every object. Every object will not be immediately pulled to this black hole, because these objects do not yet know that the black hole exists. And what they do not know, they could not physically react to. And that's the basic principle behind this law of relativity. Now, what about time bubbles? Well, let's say that there is an event, let's say an explosion. 5 seconds after the explosion, the radius of this time bubble will be 5 light seconds, because this time bubble expands at the speed of light. And what this effectively means is that for everyone inside of the time bubble, the explosion has happened. For everyone outside of the time bubble, the explosion hasn't yet happened. So after t equals 5, a guy 5 light seconds away, person A, will then see the explosion. The explosion will happen for person A. And then we expand that to 10 seconds later, so the diameter is 10 light seconds, then person B will notice the explosion. For the person B, the explosion will have just happened. But for person A, it would have happened 5 seconds ago. But for the event itself, it would have happened 10 seconds ago. And then the time bubble keeps expanding at the speed of light. Now this is how we know that our perspective of the universe depends on where we are. It depends on which perspective we take. For example, if we rewind it back to t equals 10, for example, then for person B, the explosion will have just happened. For person A, the explosion would have happened quite a while ago. And for anybody outside, let's say a hypothetical person C, the explosion will not have happened. That huge barrel of oil would still be intact, and that is his perspective of the universe. So really, the nature of the universe depends on where you are and which perspective you take, which is completely contradictory to Newton's idea of a universal stage, whereas one thing happens, it happens for everybody. No, it does not. Not yet, at least. Now, showing expanding time bubbles, this can be shown in terms of a cone, where the vertical axis is time. As time progresses, the bubble expands, and we can show this as a cone. And at t equals 0, the event occurs, and the bubble expands as time passes, so we can see this cone right here. What this effectively means is that if we have another event, let's say event A, which is outside of the cone, the explosion cannot affect event A in any way because the information would not travel to it fast enough. The event cannot affect anything which is outside of the cone because the information wouldn't have had the time to get there. We can also expand this into the past. So let's say we have event B, which is outside of the light cone, but in the past. Effectively, event B could not affect the explosion. Why? Because event B simply wouldn't have the time to affect the explosion. We can even create event B's own light cone and show that the explosion is not involved inside of B's light cone. And if these events do not fall into each other's light cones, then there is no way that they can affect each other in any way possible. Right, so that's a light cone. A very interesting kind of subject matter in relativity. And light cones can also be used in what we call world lines. And what a world line is basically the path an object takes through space and time. And of course we can draw this in the context of a light cone. And this is the example of a sensible world line, one that sticks inside of the light cone. So if we can see this person is traveling to the event and into the future, and we can see his world line going into the past, it always stays within the confines of the light cone, and that is appropriate. What we cannot see is the world line going out of the light cone from within, because simply enough, any object in the world or in the universe would not have the time to stretch this far in this little time. Because as you can see, leaving the light cone requires a certain amount of distance traveled in a certainly small amount of time passed, which would mean velocity is greater than that of light, which is impossible. Also, world lines cannot go backwards because objects do not go backwards in time, because then they would have to travel faster than the speed of light as well. Right. Whilst we're in this mindset of different states of the universe depending on different perspectives, let's conjure up a certain thought experiment. Let's say an event happens on both Earth and Mars, and you are on Earth. We can see that these time bubbles have expanded to these sufficient ranges, these sufficient radii. Let's say this person teleports near to Mars. He's around Martian space now. What he's effectively doing is he's going backwards in Earth's timeline. Because whereas the event has already happened on Earth, for him now, the event hasn't happened yet, because he is outside of the time bubble. So since it hasn't happened yet for him, he's effectively leaping backwards in Earth time. However, he's jumping forward in Mars time, because from his previous position, the event on Mars hasn't happened yet, but as he leaps into the time bubble, it has already happened. So he is traveling forward into the future for Mars, and backwards in time for Earth. What this effectively means is that the concept of a universal clock, or one timeline which characterizes the entire universe, is completely torn apart. Because different places, different things have different timelines. Depending on where you are, your timeline is going to change. That is why Einstein realized that space and time are inextricably linked. They are woven together. They cannot be separated. Space does not exist independent of time, but rather they work together in a way. So that is our little thought experiment. Now, what does this whole thing teach us? Well, one, it teaches us that there is no absolute universal clock. The clocks tick differently for different observers, depending on their velocities, which means that the passage of time is not uniform for all observers, and that absolute motion and absolute rest do not exist. Just because you see something standing still does not mean that it is necessarily standing still no matter which perspective you take. Now, thanks for watching. I sure hope you found this video interesting and helpful, and relatively easy to understand. Hopefully I didn't make it too confusing. And you know, if you want to ask a question, if you want to comment on the video, rate or subscribe, if you feel like it, do feel free. We're always open to criticism and queries. So yeah, guys, I know I haven't been posting too much recently. I'm a bit busy at the moment. Exams are coming up. But we will be coming out with more stuff soon, so we'll see you next time.